Hello everyone, my name is Matúš. I'm a senior software engineer at STRV. We are a software agency dealing mostly with US clients.
Put it closer to your mouth.
Sorry, is it better?
Yes.
And from the nature of software agency, we are dealing with a lot of code bases and with a lot of people on different seniority levels. I have encountered quite a lot of problems with misunderstanding of slices, which resulted into a lot of problems in production code. So that's why I decided to create this short presentation to explain how does slices work in background and to deeply understand what's happening and to avoid those most common mistakes. One of the most common features of procedural languages are arrays. You might say that a simple array is pretty straightforward and easy to implement, but when you are adding such a feature to your language, you need to ask yourself, do I want the arrays to be fixed or variable sized? Do I want to keep the size of that array as a part of a type? What about multidimensional arrays? And most importantly, should an empty array have any significance, any value? This is what authors of Go were asking very, very soon in the first couple of months of Go, where it was just an idea on whiteboards. And it took them around a year to answer those questions. The decision point that made them satisfied with the answer was the introduction of slices. Slices are an abstraction over static arrays, which are supposed to be flexible and extensible. When we are talking about slices, it's a fundamental part of language. You can find it across the whole ecosystem, in every library, in every piece of your code. A few of the most common ways how to create slices is to derive them from existing arrays or slices, to initialize them by literal, to declare them, or to make them. You can manipulate them in a very creative ways. And as you can see, the support for slices is pretty extensive. It's a core part of language. If we take a look at the implementation, we'll notice that the slice contains only of 3 properties. It's a simple struct that has first a pointer to an underlying array storing the data, the length of the slice, and its capacity. So if you visualize this struct, you can see that there are some squares that represent the underlying array. There is a length and a capacity. Let's start with some examples of how this works and how this affects the way the slices works. First, let's initialize a slice of primes. Let's save their length and capacity. Visualized, we see that there is a pointer to an array storing the data. We have a length, which equals to capacity, which is currently 4. Let's simplify this annotation a bit and continue. When you create an empty slice without any data, Go will take care of allocating the memory, setting the proper length, and setting the default value of the expected type. In case of int, it's a simple 0. In case you are looking to future, you would like to make some additions to the slice without having to worry about the capacity, you can provide another parameter to our make, which creates the slice, and Go will again take care and provide the capacity that is necessary to accommodate your needs. Slices would be worth nothing if you can't work with them. So you want to naturally move them around your code base, pass them into function, methods, and do some computations. So if we take our primes and pass them into function, one of the most common expectations, especially for people that are coming from different languages, is that when I pass my slice, it will get copied and I can get along. And that's a huge mistake. As we described before, the slice is a struct with 3 properties. So the thing we are copying is not the whole struct with underlying array, it's just that one header. So the copy of a slice passed to our print slice function is only the header containing the pointer, which points to the same underlying memory with its own length and capacity. This has some implications. Let's replace the print function with modified function. We will iterate over the slice and adjust the values. But now we know that our slice, called S, points to the same memory. So every change made to the S will also be reflected in the original slice passed into the function. So if we add some numbers to existing primes, the original data will get updated as well. Another common way how to create slice is by slicing an existing slice or array. So in our case, we take the primes and we want to get a subslice of them. So to get this through, we will create a new variable called subset, and we will toggle that we want all the elements starting at index number 1 all along to x minus 1, which is in our case 2. The upper number is the upper part of interval is excluded, and we get the capacity of we get the remaining capacity of the existing slice. So it's in our case it's 3. We get rid of the original S, and now we work with our subslice called subset. We can see that even the subslices are sharing the same memory as the original slice. So if we make any change to the subslice, all of the changes will be requested and modified in the original slice. There is one common misconception that is coming from comparing slices to cake. In the real, when you're slicing a cake, you can only get smaller and smaller size. But slicing in Go allows you to reslice existing slice and make it even bigger than previously than before. And you can do that up until you reach the original capacity, which is in our case 3. So subslicing does not only create a smaller slices out of the existing ones, you can also extend the length of an existing slice up to a defined capacity. Okay, now we have covered the cases when everything is great and there is a room for any value, we are just updating them. But what if I want to add a value and the slice is full? Do I get an error and am I forced to create a new slice, or will Go take care of it? Go will take care of it, and the way it's done, that once the capacity is reached, Go will copy the underlying array, it will make it bigger, allocate a lot more space to fit your needs, and points it to the new address in memory. So once you hit the limit, a new slice is created, and it points to a different part of memory. So now all the changes made to the primes were moved to a new slice, which now can be further manipulated without the changes being reflected in the original slice. You may now ask how to get those values back to our prime slice. You may think that it would be clever to just take the input parameter, modify it, and all the changes will be reflected. And that's wrong, because as we know, the slice header is copied. So any change made to that header will not be reflected in the original value. So the only effect this change will have is that instead of variable called subset, we will have a variable called S, but still changes made after append will not be reflected in our original prime slice. Another approach or idea that many developers get, that when I want to update something in Go, I use pointers. Pointers point to a memory, and I can update wherever they point to. So the idea is to pass a pointer to that slice. As you can see, and as I can tell from your faces, code got a lot uglier. And I don't think that's the right way to go. While it's technically possible to do it this way, the Go tooling and the Go ecosystem isn't adjusted to deal with pointers to slices. It works only with basic slices, and that's why there is a recommended way you can see in the Go ecosystem, and that is the returning of updated slice. So once you make any changes, you grow the slice, you shrink it, or you adjust the values. It's a good practice to return the updated slice, so it can be saved in the original slice and stored as you wish. With this update, all of the changes are reflected back to the original slice, and we can go along. But what if I don't want to make changes in the original slice? All of those examples were considering the fact that I am willingly updating the original slice. But if I want to decouple it from the one that was passed into function, you need to make a copy of existing slice. To make a copy of a slice, you just need to provide an empty slice that has sufficient space and tell Go to copy values from an existing one. This way, you have an independent slice. You can do whatever you need to without affecting anyone that passed the value to your function. Now that we know that how the slices behave, that they are not copied entirely, but only the header is being copied, there are 4 recommendations that, when followed, will help you to avoid 99% of the most common mistakes. First one of them is when you want to change that your slice is empty. Having pointer in underlying struct may lead you to this nil check. You have to realize that there is a difference between a nil slice and an empty slice with 0 length. Nil slice is slice where array points to nowhere, which means that the pointer is nil. It has a 0 length, it has a 0 cap, but you can work with it. Go will take care of it. Go will grow it as expected. The only difference is that the array points to nowhere. When compared to an empty slice, it has mostly the same properties, but the array points to some kind of memory that is not being used by the slice. And that's the difference. Unless you really know that you want to check for the slice being nil, and you expect that behavior, which may be different in some kind of libraries like JSON encoding, it's always recommended to check for the length instead of slice being nil or empty. The second recommendation is that you have to keep in mind that when you are passing a slice into function, and that function modifies the slice, you are modifying also the original value. If you want to avoid this behavior, you need to copy your slice, make a separate independent copy, and do your stuff with the copy. If we continue with the changes to an existing slice, there are some cases when you need to adjust the length by either making it smaller or appending some elements. The third recommendation comes with returning the updated slice every time you update it. Unless you return this updated header, this updated slice header, there is no way to tell the original value that something has changed. And the last one that is coming from a real project, to illustrate the issue, there was this service that was categorizing files. You can imagine your school folder with 200 gigabytes of data, where you just want to read the files, you want to save the paths, and you want to read only a header of file. This way, whenever someone asks for a file, you can provide some metadata, some information about size, and whatever is needed. The flow is pretty simple. You don't want to mess with the readers. You just read the file and get first couple of bytes. No big deal, right? But some of you already spot the mistake. From what we learned, we know that we store the data in an array, in a slice. This slice has a capacity and a length. And when we slice this existing slice, we shorten the length, but we keep the original capacity. And this led to a lot of problems. It was a bunch of small files, and the memory kept constantly growing until we reached out of memory issues, only because, along with the header, we were dragging all of the file contents in the background. It's still claimed by the slice, so it cannot be garbage collected. And with this approach, you are going to encounter many issues. So if you are interested only in a small part of a lot bigger slice, you should always copy those values and get rid of the rest. And that's everything from me. Thank you for your attention. And if there are any questions, feel free to ask.